Welcome back, Flameborn. Today we're going to be taking a look at some of the work that's going on to help make Enshrouded run better. This is a topic that's very important to us. So in today's video, you'll be hearing from the tech team that works on Holistic, the in-house engine that's powering Enshrouded.
Hi, I'm Julian. I'm the technical director here at Keen Games. Performance is super important for us. We want as many people as possible to enjoy Enshrouded. But Enshrouded is a very demanding game, featuring a fully modifiable open world with a huge view distance on top of a day-night cycle and players creating huge spaces. This is why we have our custom engine Holistic, without which Enshrouded wouldn't exist. We are confident that the 1.0 version will be considerably faster than the previous versions in many areas. Lots of GPU optimizations happened and are still being worked on, as well as optimization on the CPU side. Water simulation, anti-system optimization and more. We use less memory now and the network code is improved. And as always, we will continue working on all performance topics, even after 1.0. Today, we would like to share some of our recent work with you. The brick renderer to improve performance while increasing details shown from afar. A technique to improve performance of our sun shadows. The world SDF data structure to speed up our global illumination. Our current plan to improve the performance of point lights, reducing VFX permutations to improve shader compilation times. Let's dive into a bit more detail, starting with Florian talking about the brick renderer.
Hi, I'm Florian. I'm a senior engine and graphics programmer, and recently I've been working on the new terrain system for Enshrouded. We call it the brick renderer. What does it do? Well, one of our main problems with world geometry is that all of it can be changed by the player. Sometimes voluntarily, sometimes by accident, and you can see the whole game world from some places. So we absolutely want to keep a high view distance, but we were not happy with the detail loss in the distance. Converting all this voxel data into triangles is a big bottleneck, especially when we want to increase the details seen at a distance. Instead of converting voxel data into triangles, we now create little bricks filled with a compact surface representation called sign distance fields. We can stream them in or create them on demand based on GPU feedback. The process of creating the bricks is much faster than creating triangle meshes because we use the sign distance field as an intermediary step to mesh creation. The small bricks are very nicely suited to culling mechanisms, so we submit less work to the GPU than before. Additionally, it lends itself to using a visibility buffer internally, which reduces the memory bandwidth because we don't write out so much data all the time when multiple bricks overlap. The brick renderer is quite a bit faster, depending of course on platform and GPU, while allowing much higher detail at a greater distance. Let's talk about shadow optimization now. Sun shadows are notoriously expensive in an open world game with a day and night cycle, because they keep changing, and even more so when the geometry can change through animations or player interactions. One of our systems to render realistic shadows are our cascaded shadow maps, which have been a major performance bottleneck in the past. Most of the space in the shadow maps is actually not needed, because those areas are actually not visible from the player's point of view. So the idea is to figure out what parts of the cascades we need to fill. We do that by first rendering the depth buffer of the main view, and then using that to mark places in the shadow map we won't need. This improves culling efficiency massively in lots of places, leading to a great speed up.
Hi, I'm Jacob, senior graphics programmer working on global illumination, reflections, vegetation, and Raytracing. Thick forests and big player builds can have thousands of models, with many of them overlapping. Think of whale water basin or your favorite contest-winning entry. Our previous solution was testing all object sign distance fields in array path for intersection. As many trees and objects overlap, this became a lot very quickly. So we decided we need to do something about it and fully rewrote our Raytracing backend from scratch. Our new system, called Ruled SDF, combines all objects into a central data structure, leading to just a single intersection lookup at any world position. It also optimizes data bandwidth by a factor of 10, while reducing the number of nodes we need to traverse considerably. Previously, only doors and big trees were present in the ray-traced world, but with the Ruled SDF, we are now finally able to add all static objects bigger than, let's say, a bottle, into the ray-tracing world. This affects global illumination, as objects block light. point light shadows, as barrels and poles cast shadows now. And reflections, of course, as all static objects are reflected even when out of screen. Performance-wise, we get a 2x Raytracing speedup in simple scenes such as the top of a mountain with no trees and models around. Up to 3 to 4 times when trees and forests are nearby, and even reaching 8x speedup in thick bamboo fields. Another bottleneck in reaching our performance goals are the point light shadows. Lights are currently shooting rays and creating a shadow map per light, leading to millions of rays per frame. These rays also cover a lot of area that might be out of screen or occluded. All of this just to support around 100 to 200 lights around the player depending on the settings. Therefore, we are working on a new system that is raster based, shooting shadow rays directly from screen pixels to light sources, considering only places that are actually used and visible. By moving to screen space and picking only the best lights with stochastic, we should be able to support over 32,000 lights while keeping a stable cost. We are still working on this and hoping to be able to include it in time for 1.0, but if not, it will be included a bit later, as we always try to improve our tech.
Many of the animated objects you see in the game are visual effects, even when they don't look like them, such as the factories or the line of the grappling hook. These were created by our tiny VFX team using a GPU-driven particle system. This process resulted in thousands of different unique shaders. We are working our way to combine lots of these into fewer, more complex ones. This will reduce the number of the shaders dramatically and will speed up the initial shader compilation time. But it's a lot of work because we can't break the existing VFX, and as I mentioned, we only have a small VFX team, so this will be an ongoing effort. The shaders we ship with the game are not the final ones. Each player's GPU driver needs to translate them into the installed GPU's machine code. This process needs to happen again whenever we change the shaders or when the driver updates. This is not an issue on consoles because the same console model all share the same hardware, so we are able to do the compilation process offline and ship the final GPU machine code to you.
Thank you for sticking around for such a long video. We know this topic is a bit technical, but we thought we could provide some insight into what makes Enshrouded tick and what we're doing to make it even better. We hope that you're excited for the full release of Enshrouded on PC and PlayStation 5 on October 15th. Check out our channel to find more of what we're cooking.